No. Any other doubts? We could discuss on more specific doubts on the assignment, not assignments, I mean the homework problems or any of the class also.
So, suppose you want to know the Lipschitz this, let's say, composition of two functions. Okay. So, the functions have to be bounded from that to happen. But do the gradients also have to be bounded? Do they have to be Lipschitz continuous?
We have to do Lipschitz right?
Yeah.
So, gradients has to be bounded for each of them.
So, it has to be Lipschitz continuous.
Yeah. Anything in the projects, if you have any doubts, we can also discuss that. Projects specific.
Yeah, we have to when do we have to submit the project any abstract or what we are working on?
So I think those are decided, right? Because you are already designed. I think there will be after during the seminar. I think we plan to host a preliminary sort of project review. I think. So there, I think you can submit as the abstract or the project.
Okay. Because suppose we explain a project and then if you feel like it's not up the mark.
Yeah, yeah. So I would say like yeah. So maybe before we start the, I guess like those things can be cleared out during the seminar itself. I think. But I would request like if, all can we would open up a sort of a form where you can submit the preliminary version of the provincial and abstract. And it would be ideally like 2 weeks after midsummer once.
I think this I can connect this thing here. I think Professor Ganesh is on the call, so if, I think he can. There is one homework problem. I think last on Monday class. I think probably I think we could discuss that. So I think he can screen share. So if you have any questions specifically for him, you can also ask right now. So I think this was the last time's homework problem. So this was the last week's homework problem. So any questions here, like specific doubts in the settings, like? So yeah. in some doubt sessions. So I just recap a bit on how we got to the homework problem was that if you use strong convexity in conjunction with L smoothness to get a sufficient condition where the convergence steps, the total number of convergence steps is greater than or equal to some logarithm of 1 by epsilon, where epsilon is some fraction value. And so anyone was able to solve this thing, or anyone had any sort of like any progress on this? Like, so I think like the expression on the yellow highlight, I think you can use things like telescopic summing where you cancel out terms and you just are remaining with the first and the last terms mostly. So there, if you utilize the and basically due to strong convexity, you have a corresponding much more stronger lower bound that you can utilize directly as shown in the figure in the highlight brown. And so using both of these two together, using both telescopic summing and the stronger bound, you can rearrange the terms to get a much more tighter bound. Um, so I think though if you use those the strong convexity assumptions and all, so you can get to a better bound. So that was the aspect. So any questions here, like sort of like any doubts how to use specific tools? Because I think in the exam, I think we would have similar kind of questions where you would be requiring to use specific tools like telescopic summing and all. So, yeah. So last class, I think gradient descent. So I think yeah. So last class, I think gradient descent up to which point was covered mostly. Uh, so I think accelerated gradient descent and all those things are not covered, right? Yeah, I think you can expect some questions in terms of where you have some functional form of this whether a function is strongly convex or convex. You have to prove and sort of write whether it's convex or Lipschitz smooth or all. And also in under those constants, so like what the convergence steps looks like. So those are some of the questions you can think of that might become. Yeah.
We also have to prove that it's not Lipschitz.
No. So it's just that I think so. Lipschitz, so convex, strong convex, Lipschitz smooth, Lipschitz continuous, and Lipschitz smooth. It's like a range. You can just focus on just proving one of them. Not that you have to prove the upper level. Yeah, I think so. Professor Ganesh actually wants to run through the steps of the homework problem step by step. So maybe I think you can follow, and if you have any doubts at specific points, you can just ask. So, right. Yeah, I think you can go ahead. So we are using 1 and 2 to sort of using the second option 2 for strong convexity, the bounds, and the one from the telescopic summing setup. We are using it to just find out like at xt and the optimal fx star, what is the upper boundedness that we are getting, what is the threshold we are getting. And you can rearrange these terms to get the final sort of term, which is xt plus 1 minus x star. And you want to actually utilize, you want to find the term t, small t, in terms of capital T, sort of by summation, summing up from 1 to capital T, so as to see what is the total number of convergence steps you require. So this is my final term, which I'm getting, which is in which I'm getting here, where this fx star minus fxt basically is the value of the optimal solution minus the corresponding kth step function value, and corresponding coordinate points are the norm of them is bounded by the RHS of the equation. So next slide, I think. Yeah, you can go ahead to the next slide. So there is a marker or something here. Right. So I think this portion. So now continuing from the previous step, I think this is where we left off, the final term that we are getting, and then just give me a moment, I think. Which is the slide number for this? So I'm trying to open the slide actually. 13. Okay. Okay, I think I'm presenting my screen. Okay, so I'm at. Okay, so I hope this screen is visible to you. So this, if you see, there is a term 1 minus mu gamma as a coefficient on the right hand side, and so if you if you divide both sides by this 1 minus mu gamma by t plus 1 to the power t plus 1, and then do telescopic summing on the top of that, you can if you see like you are so what I want is like the terms in blue, whether we can show that these terms are like negative or not. So in that setup, like if we can show that, so we can decrease the sort of like the yeah. So if these terms we can show if it's lower bounded, if it's upper bounded by 0, and then we can utilize the L smoothness setups directly and sort of to get the term more simplified. So we are dividing by 1 minus mu gamma t plus 1 on both sides, and final expression is that you get the terms cancel out due to telescopic summing on the LHS part. You are left with x capital T minus x star to the power the squared by 1 plus mu gamma t to the power capital T. and this is upper bounded by this term in blue plus your the deviation from the original point x0 to the optimal x star, and we have to show like this. If you can show the blue term is non is a negative number, then we are done with the following upper boundedness on the RHS side, which is just x0 minus x star, because this term is less than equal to 0. So in order to show that, if we can go to the next slide. So so this is like probably may not be evident during the proofs right away. So it's just that how so you can think of it like my end goal is to upper bound the RHS side by x naught minus x star, which is my starting point and the optimal final point coordinate which I'm trying to reach. And this has to be upper bounded by that. So in order to do that, what sort of tricks I can use? One is we did this telescopic summing. The other part is of dividing both sides by 1 minus mu gamma to the power t plus 1. And so if you can go to the next slide. Right. Can you go to the next slide? I think. Can you go to the next slide? Okay. Okay, so we had from the last slide the top upper bound, which we got from xt plus 1 minus x star. And also for Lipschitz smooth function, we know that I can upper bound f of x t plus 1 minus fx t by, yeah. Can you click on? So can you please give me the lecture slide number? Like, is it 13 or 14 right now? 14. Yeah, I think I found the slides. So I'm actually moving it by my hand. Okay, so right. So let me. So okay, so we know from Lipschitz smooth definition, like we can write f of xt plus 1 minus xt as the gradient with plus this L by 2 term. And we know like xt plus 1 minus xt can be written as gamma squared gt due to the convexity aspect, and I can upper bound that itself because xt plus 1 minus xt is basically your um, your so you can, due to convex the definition of convex function, you can directly write it as the gradient gt norm. So I'm able to screen share this. Okay. Yeah, so we have the final bound in the color red, which is this setup, and then as mentioned, like what we wanted is this final expression here, which is this term in blue, to sort of if we can upper bound it as by 0, and we want to also like sort of simplify this particular expression in blue, which so. Uh, uh, one aspect you can think of is that f of x star is always less than equal to f of x t, because it's that the optimal point you want to calculate the function f, and it's less than the any other point in any other point. So this first term, which is f of x star minus fxt, is a negative term, and this if I the term on the right side, which is gamma square gt square, is anyways positive term. So I would have to sort of if I substitute, let's say, gamma equal to 1 by L, then what's the sort of upper bound I can get here? So that's my that's something I want to check. So and sort of like we want to minimize this term. So this blue term we want to minimize, and one aspect to do that is like you can just you can just take a gradient of the entire term and equate it to 0. And I want to do that with respect to gamma. Like with respect to gamma, what is the minimum value I can get for this blue term? So for gamma equal to 1 by L, I think this was already shown in previous portions of the class. For gamma equal to 1 by L, I have f of xt equal to 1 by 2L gt norm square, and this is and if I directly apply here, let's say for gamma equal to 1 by L, I take the equation in red, and if I try to minimize that, and I know that f of x star is less than equal to f of xt plus 1, because it's a convex function, I can write it as since f of xt plus 1 is upper bounded by the red term, and f of xt plus 1 is anyways greater than equal to f of x star. So I have the final bound, which is that f of x, it's both sides bounded by f of x star and f of xt minus 1 by 12 gt square. Now we want to show that this term 2 gamma f of x star minus f of xt, which is actually the numerator term in this blue highlighted portion, is less than equal to 0 or not. And I take the step size gamma equal to 1 by L here, and if I just replace with gamma equal to 1 by L in the equation, what I get is I get minus 1 by L gt square, the first term. This is basically from the fact that I just showed here, like f of x star minus f of xt is less than equal to if you just take the extreme LHS and the extreme RHS portion, f of x star minus f of xt is upper bounded by 1 minus 2L gt square. And if I just directly substitute that in the brown shaded equation here with the upper bound, I get a total term to be upper bounded by 0. So I'm done with the fact that the numerator term is upper bounded by 0, and so whatever, because the denominator part is a it can be any and it's positive in some sense, because and so if I can directly show due to the numerator part that this entire expression is upper bounded by 0. And so so finally we have the following, that xt minus x star whole square is would be equal less than equal to 1 by mu by L xt minus x star, because I'm displacing gamma by 1 by L. So in this case, and if I replace gamma by 1 by L, and the fact that the first the brown term and the yellow term are both upper bounded by 0, so I can directly write it as the following expression. And then I also know the fact that the the Hessian is upper bounded by this sorry. Yeah, so the term mu by L, 1 minus mu by L, it would be between 0 and 1, because mu is less than equal to L due to the fact that the Hessian is upper bounded by Li and lower bounded by mu I. And so this term 1 minus mu by L is lies between 0 and 1 as a fraction. And now if I this is from, I think, I don't yeah. So there was this covered last time, like this Q linear convergence and all on Monday's class. This was covered, or okay? Right. So I think there is a sort of it's getting cut out somewhere. Right. So I'm actually like trying to skip this thing because it's not. Maybe I will just come to this thing once when it's actually used. So I had this term xt plus 1 minus x star less than equal to 1 minus mu by L, this thing. And analogous to telescopic summing, we're doing something called telescoping. Like, you can think of it like as a telescoping product actually, where you have this multiplication of terms from t equal to 0 to t minus 1. And many terms gets cancelled out, and you are finally left with this final inequality, where the final step term and deviation from the optimal coordinate with the final step coordinate is upper bounded by this 1 minus mu by L to the power t. And this fraction is much more smaller because 1 minus mu by L is within 0 and 1. So anything to the power of some positive integer, it's anyways a much more smaller value. So right, so so what we want to have is that f of xt should be as close as possible to f of x star. It may not be the case that you are actually able to reach that, because it can think of the function as a, let's say, a sudden spike, let's say, where the optimal term occurs at only a specific point, and you may not be able to reach that term. But what we want is that we want to reach as close as possible to that optimal value. So for example, this is one sort of illustrative example is this term where you have x star as the optimal global optima, and xt is some neighborhood point, and what your function value is not actually equal to the optimal value, but you are trying to reach as close as possible to that. So in that setting, like let's say, like how can I do that? So I can assume that f of xt minus f of x star is upper bounded at max by some epsilon sort of, and I can utilize those setups to come to a final convergence bound in terms of epsilon itself, where you can write something as order of log of 1 by epsilon, because the logarithm terms comes here because there is a power here, 1 minus mu by L to the power t. So that's why this logarithm term, you can think of why this might come. So right, so in our final step, like we want to combine smoothness also, and the fact that the gradient at the optimal step is 0, because it's because it's an optimal point. So I can write it as f of xt minus f of x star just by the definition of Lipschitz smoothness. And which is equal to L by 2 xt minus x star, because f of x star gradient of f of x star is equal to 0. So the first term on the RHS side is set to 0, and you are only left with the second term in the RHS side. And now I know that f of xt minus f of x star is somewhat like L by 2 is upper bounded by L by 2 xt minus x star. And if I again utilize the equation at the top, I can write it, simplify it, and get as upper bounded of L by 2 1 minus mu by L to the power t x 0 minus x star. So there is a necessary condition, because because it always holds true. Gradient of f of x star is equal to 0. And if I replace xt minus x star, x0 minus x star as the sort of the you can think of the radius, I think, the bound, maximum bound you can think of as r, let's say. And so you're left with the term as L by 2 1 minus mu by L to the power t r square. And so this is like a, if you think of it as a Euclidean ball sort of, where your center is at x0 coordinate and your optimal point lies on the diameter of the Euclidean ball. So it would be it would be your x star is your optimal point, and so this radius is set to r, and we want to see like we also, as I mentioned, we also have this uh, diagram, I think, somewhere back, where we showed that um, the upper boundedness of a function fy is upper bounded by the Lipschitz smoothness and the strong convexity setups. So this you can directly utilize this thing because we have this term mu by L, so which we have here. So and I mentioned like mu by L is a fraction. So let's say yeah, so right, so this is my final expression term that I get, and to get an error of epsilon, we require that this f of xt minus f of x star is upper bounded by some epsilon term, which I mentioned, like we want the final convergence value to be as close as possible to the optimal value. We may not reach that value, but we want to be as close as possible. So we defined any convergence steps with respect to this epsilon term, and this upper bound is less than equal to epsilon, and you can directly solve this thing and get that t is lower bounded by some logarithm term of r squared L by 2 epsilon. So and this is this L by u term again comes into picture here, because there is a L is your quadratic upper bound and mu is your quadratic lower bound here, and so it's pretty easy to do some kind of synthetic analysis here also, like where you have epsilon equal to 0.01, then in those cases how many iterations you might need. So some questions might be like this also, like where you, these are pretty simple like setups, like you just have to do some number calculations here, that's all. So in the case of smooth assumptions like Lipschitz smooth assumptions, these are the number of iterations. In the case of just Lipschitz continuous, what are the number of iterations you, those kind of analysis you might get asked. Right, so I think that's all. I think that's completes the proof, I think. Yeah. So right, so these are some of the final sort of corresponding functions, properties, and corresponding convergence steps that you might achieve with specific value of step sizes. And so Lipschitz continuous functions, with step size of r by b to the into root t. R is basically your radius that you define. To achieve an eta approximation solution, you would need at least r squared b squared by epsilon square iterations. Similarly, you can think of other variations like smooth functions, smooth plus strongly convex and all. And the basic takeaway here is that so the as this value of epsilon, if you see the examples here, like 0.1, 0.01, and 0.001, and so in those settings, if you see the iterations are increasing in some kind of like by some kind of additive constant, like 8.49 to 13.49 to 18.49. And so the basic takeaway here is that in case of strongly plus smooth convex smooth case, your number of iterations increases by some additive constant. So some analysis you can think of in case of just Lipschitz smooth or just strongly convex settings, whether you are still getting an additive constant or something else. Those kind of settings you can think of. Okay. Okay, so yeah, I think that's all. I think we can stop here. This is mostly up till for your midsem syllabus. So if you have any sort of doubts in the previous proofs or any specific sections, let me know. We could take up those up right now. Yeah, I think that's all for the proofs. I think whatever we had to show for today. Any specific doubts in the previous proofs you want me to go through, or yeah, if you have any questions in today's proofs also, you can ask sort of anything. If you felt that I've skipped, you can ask. But yeah, so this portion I think is the non-trivial portion because in order to get that sort of intuition, like why this blue term, how you can bound it by upper bound by 0. So you can think of way of doing this by sort of like going backwards, like what is the final solution you want to have, what is the approximate bound that you want to have, and you can go backwards and sort of try to figure out that this blue term has to be upper bounded by some kind of 0, it has to be non-negative in some sense, in negative in some sense. So and specific tricks like telescopic summing and telescopic product are some of the things that people use to cancel out terms and get the final and the initial coordinates. Right. So I guess like that's the only non-trivial part here. Everything else are mostly like algebraic manipulations. Yeah. Anything here specifically? Any questions here? Like yeah. Okay. Yeah, I think so. That's all I think here. But so you can think of some more examples, like let's say the function is of a special term, like so there are specific. I don't know like if people have gone through specific metrics like L11 and all already are familiar with them. So there is one specific setups I think we are also working on, and is that some of this distribution divergence can be thought of like this thing called Renal divergence, which is basically alpha divergence kind of things. So there, like this kind of proofs actually come up a lot, where varying the value of alpha, you can get either the standard KL divergence or Hellinger distance and all those things. So in those settings, how if you want to minimize the KL divergence or the alpha divergence, in those settings you can directly use this kind of proof techniques to get to convergence steps and all. So those are again like has those properties of Lipschitz smooth and all. So that is one takeaway, like where you can utilize those things. Yeah. So right. So I guess any specific questions? Any other questions here, like? Yeah.
It's not restricted in the sense, but the sub-difference, because sub-variable, can it ever be empty? Any, there are function does not have any sum.
Uh, if you have a Dirac delta function, which is basically all probability mass into one setting, that has infinite differentials, I think. Yeah. Yeah. What about y equal to the uniform distribution? Uniform. line y equal to 1, let's say. So there are two extreme cases. One is a vertical line, one is a horizontal line. Is there a subdifferential there? Like, there is, I think. Yeah. So the differential is 0 here because it's a constant function, but the set is not empty. Yeah. So I think for any function, I think unless it's a yeah, for any function you would have a non-empty differential sub-differential. Right. For any real value functions. So I think for even for this, or we discussed mostly for convex functions here. I think also for non-convex setups, because in real world scenarios, many functions are not always you would see this convex properties, this nice properties that you see here, and in many cases those things are hard to sort of prove also. I mean, this convergence proofs and all. In many cases you have like bounded convexity where you have in some bounded region some convexity. It's not globally convex, but it's at specific regions it's convex. So there is this concept of restricted smooth convexity, restricted smooth concavity and all. That means like where you have in specific restricted bounds where you have this convexity convexity properties. So there these bounds change. Like you have to whatever the sort of the assumptions that you're taking in the inequalities here, that has to be done for specific bounds, and proof structure changes that way. Even for inequalities like Cauchy-Schwarz and all, like I think that's not possible across all the entire region, sort of only at specific regions. Right. I think yeah. Any other questions in today's proof or any other previous proofs? If you have? So you can expect like something similar in the proof structures, but maybe some different structure in the function f, let's say, or some other properties which are not covered that much in the class, or maybe specific steps in the proof you might be asked to fill in the blank kind of thing. So, or maybe I think there was some question where we had some error in the proof, like in the proof steps, some error. We have to identify that. So those kind of things you can, So I would say like go through the proofs, write it by hand. I think helps to understand these things. And if you're in many cases like some question I remember, I think in our midterm also we faced that was that there was a question where you have the proof steps and 2-3 steps are missing. You have to fill in the 2-3 steps. Like, so how do you do that on all those things? So right, exactly. So wrong assumptions or wrong steps like that. So you have to identify that. Right. So I think that's all. Anything else like specific? Yeah. Yeah. Any other point? Yeah. Midpoint convexity is usually taken because it's easier to show because it's a specific use case of the general convexity, right? The special instance sort of lambda equal to half actually. That's the only special thing. So I can take lambda equal to anything, 1/4, 3/4, anything. So I can take lambda equal to half here, and because it's convex everywhere, so that's and okay. I guess that's all. If there are no doubts, we could end. I think. Okay. Okay. I think. feedback form. I think it's before midsem. I think so. You can submit. Yeah, I think you can submit via ASC. I think there is already a form floated there. So just if you can confirm, one of you, if there is a, if you can see the form. Do you see the form?
Can you guys check whether you can see the
In other courses, they put out announcements in Moodle.
Yeah, in announcement, I think we can put out.
no, if that is not there, we can float a form, right?
Right, we can put a form.
But then it's not anonymous.
No, it's not anonymous, right?
No, see,
AC, there is a.
in
Yeah,
Yeah, I think there is a, on your AC portal, there is a feedback form. So we made some feedback form. You should submit. One is post. I think midterm feedback is the one. Yeah, I think that's all. I think try to submit it before midsem. I think because deadline is before midsem. So I think yeah, I think we would resume meetings.
I think, can you hear me?
Yes, yes, I can hear.
It's not more informal. I don't know, can't hear. It's just very bad throat. But you can just say a small. I've written on the chat just a small sheet of paper. You can give the informal feedback on text. That's also good enough. I mean, since
Okay.
just they're leaving in a small sheet of paper.
Okay, sure.
If this is more informal. Then it's just encouraged by the.
Okay. So do you have a sheet of paper? Anyone has a sheet of paper? This is blank.
it's printed ones.
No, I don't want printed. Okay.